Well, good afternoon. My name is Sam Chan, and I'm the Broader Impacts Team Leader for the National Science Foundation funded Willamette Water 2100 project. So on behalf of the NSF funded project, as well as Geosciences and the Oregon Climate Research Institute, which is headed by our speaker, Dr. Phil Mote, I'd like to welcome you to today's webinar on the National Climate Assessment Project that Dr. Mote has been co-leading and doing much of the writing on for past, 2 years, Phil?
3.
3 years. And Phil comes to us from the University of Washington, where he earned his doctorate degree. But over the past 2 years, Phil has produced not just this National Climate Assessment Report, but he's actually been involved in 3 other national assessment reports on top of his research duty and running the directorship. So the reason why we invited Dr. Mote here today is because his work that he shares with his colleague along that's been funded by the administration is one of the first pieces that really puts an application phase to what climate change research significance means. And so without much further introduction, I'm going to introduce Dr. Phil Mote with the Oregon Climate Research Institute at Oregon State University.
Thanks, Sam, and thanks everybody in the room and online. So if you have a burning question or point of clarification as we go along, by all means raise your hand, and then we'll have some time at the end for general or specific questions about the content as well. So as Sam noted, I was involved in the third National Climate Assessment, which was released on May 6th. I was involved both as a member of the steering committee. This is the largest committee I've ever served on, 60 people. It was not intended to be quite that large, but it grew by accretion once word got out that this was happening. And I was also an author. I co-led the Northwest chapter, which was one of the chapters. I brought along so the report is available online at globalchange.gov. The 30 chapters are all electronic, and you can also print PDFs, but they're all hyperlinked. So when you open a PDF of a chapter, and it makes reference sometimes to other chapters, you can click on that and get lost in the maze of other chapters. But they also produced this highlights report, which is 137 pages. And an overview document, which is only 20 pages. There's also a 2-page summary of the Northwest chapter, as with all the other regional chapters. But I will also talk a little bit about this companion volume, which is a 230-page report, Climate Change in the Northwest, Implications for Our Landscapes, Waters, and Communities, which was co-edited by Megan Dalton with the Climate Change Research Institute, and also myself and Amy Snover, who co-led the Northwest chapter. So there was a lot of overlap between the Northwest report of the National Assessment Report, the Northwest chapter of the National Assessment Report and the Northwest report. A lot of similar people involved. This was published by Island Press last October, and you can order a copy online. There's a link from the OCCRI website, occri.net. So I want to say just a little bit before we start with the content about the NCA process. And I included this photo of Kathy Jacobs, who was the overall leader of the National Climate Assessment this time around. Kathy took the charge to produce a report and really transformed it into a process unlike any report process I've ever seen. She was very committed to public engagement and sustained assessment. So we not only had 300 authors of the 30 chapters and this 60-member advisory committee, we also had listening sessions around the country during the report development process, basically to make sure that we were covering all the important topics. There was also a request for information where any interested party could submit a technical input report. And those were due in March of 2012, and they were intended to be available to all the author teams of the chapters. And we as authors were charged with looking at all the technical inputs that were provided to make sure that we had a really comprehensive process. This contrasts with the IPCC, where we simply go out and sort of comb the literature ourselves and do the best we can to cover the relevant topics. In some cases, these input reports brought to our attention things that we might otherwise have missed. I also mentioned that Kathy was very committed to a sustained assessment, so not just producing an assessment report that represents the state of knowledge at a point in time, but also building the capacity for longer-term engagement and continued sustenance of the relationships established between academia and the research sector and the more real-world sectors. So even though the report just came out and there's sort of a sigh of relief, and Kathy has moved on and is back at University of Arizona, there's still a sense that there's momentum and things that need to continue happening. Some things that were new this time around, there were new topics covered. I mentioned at the beginning this was the third assessment report. I was also involved in the first assessment report, which was released in the year 2000. The topics here, oceans, coasts, urban, rural, and land use, were all new. We also had a couple of chapters that looked at interactions among sectors. So for example, energy, water, and land. If you try to solve the greenhouse gas problem by growing more biofuels, that places demands on land use and water. We also, as I mentioned, had digital products, an interactive website. So there's the highlights document that I waved at you. The Global Change Information Service is a larger enterprise of the federal government that this is part of. Each chapter also had what's called traceable accounts. So if you actually download one of the chapters, for instance, the Northwest chapter, the first 11 pages is content. Then there's about 6 pages of references. And then there's about 10 pages explaining how we reached the conclusions we did, what information we considered, and so on. There was extensive review. There was a single review period when the agencies, because this is a federal report, the agencies reviewed it. There was also public review, which was surprisingly very constructive. Occasionally these things can get taken over by counterproductive elements, shall we say. And the National Research Council, National Academy of Sciences, also reviewed this. And in fact, the dean of my college, Mark Abbott, was on the committee that reviewed this. And as with IPCC, we had to document how we responded to every single one of the comments. I think there were about 5,000 comments, which is only a tenth as many as with the IPCC report, but still very, very helpful. So the headline document really is intended for a completely non-academic audience. So I'm going to show you the sort of very, very simplest representation of the findings, which consists of a very short, snappy statement and an eye-catching photo. So those of you in the room, and I know there are at least 3 who are climate communications experts, this kind of thing makes us scientists uncomfortable, but we recognize the value of the short, snappy statement and the photo. So one of the main points is that climate change is not something that's way out in the future. It's, quote, moved firmly into the present. So here's, a guy clearly dealing with a foot of flooding. Americans are already feeling the effects of increases in some types of extreme weather and sea level rise. So this, I believe, was a photo from after the storm surge associated with Hurricane Sandy. We don't say that this was definitely because of climate change, but these types of things are occurring and they're affecting Americans. And those of us who were involved in media work 2 weeks ago were trained to say this is affecting Americans now in just about every paragraph. That was kind of the point of the report. Impacts are apparent in every region and in sectors including health, water, agriculture, energy, and more. So this is the sort of iconic, farmer looking at his dried up field. Whoa, okay. And there are many actions we can take to reduce future climate change and its impacts, and also to prepare for the impacts we can't avoid. So on the left, an image of solar panels, alternative energy. On the right, a bigger culvert meant to handle the larger floods expected in the future, that kind of thing. So, Getting a little more now into the science, and some of this will be very familiar if you've followed the field, read IPCC reports, things like that. So numerous independent lines of evidence demonstrate that warming has occurred, and human-induced warming is superimposed on natural variations. So we don't expect every year to be warmer than the last in every place. There are variations, and they may mask the overall rising trend from time to time. There are at least 10 lines of evidence that the Earth is warming. So the black arrows indicate reductions in quantities, and you'll notice those all have to do with snow and ice. And the white arrows indicate increases in things that all are connected to temperature in some way. So the ocean heat content is rising. That's causing the sea level to rise along with the melting glaciers. The sea surface temperature is rising. The air temperature over the oceans is rising. The content of water vapor in the atmosphere is increasing. Temperature over land and in the troposphere are all increasing. This is not exactly a solid demonstration of the human impact on climate, but I'll get to that shortly. Carbon dioxide, indicated by the blue curve and the axis on the right, has increased from its pre-industrial values of about 280 parts per million, or 0.03% of the molecules in the atmosphere, to nearly 400 parts per million today. And the temperatures, the global temperatures, as indicated by the bars, have also risen. You can see that there was a bit of increase early in the 20th century, and then a sort of level period, and then much more increase after about 1970. Just another piece of evidence, the Arctic sea ice has declined substantially. The September ice is shown by the graph on the right, and you can see that the value in 2012, which is the last data point on there, was less than half the average value in the beginning of the satellite era, the 70s and 80s. So quite a large reduction, and the map on the left sort of indicates where that's occurred. Most of the loss has been over on the Russian side of the basin, so now the Arctic nations are beginning to prepare for the opening of regular shipping through the Arctic, and the Coast Guard is figuring out how they can patrol a section of coast that used to be unnavigable. Human activity is the primary cause, certainly of the rise in carbon dioxide through activities such as those pictured here, but also, and this is a little bit harder to demonstrate but still pretty solidly shown, also of the increase in temperature. That humans are responsible for raising the greenhouse gases is clear if we simply add up what we've dug out of the ground and burned. Starting with coal, these are the annual emissions dating back to 1850. So initially we were just digging up and burning coal, and then gradually more and more oil, followed by natural gas starting in earnest in the 70s. And natural gas is now a larger component of the total. Construction of cement also liberates some carbon dioxide the production of cement liberates carbon dioxide, so that's shown here as well. But the global emissions of carbon dioxide are now about 9 gigatons of carbon per year. So this is a very, very big increase. And if you remember back to that temperature curve, most of the increase in temperature occurred since 1970. You can see most of the carbon dioxide emissions happened since then. The big ramp up in especially in oil consumption. So this is a fairly sciencey version of a graph. I'll show the final version that appeared in the report. So this was the version that went out for review a year ago in chapter 2, showing simulations of 20th century climate using climate models, first with just the natural forcings included. So those are the blue curves. So the distribution is meant to show what fraction of model simulations fell within each of those color contours. And you can see that the blue really departs quite a bit from the observed, which is the black, starting again, in about the 60s or 70s. Whereas if you also tell the climate models about the increase in greenhouse gases and other human-caused forcings, you get the red shading, which you'll notice virtually every year in the real world falls within that distribution of modeled temperature. You'll see in some places where there's a dip in both the modeled and observed climate. So for example, here in 1982 and 1991, anybody know what happened in those 2 years that was special? Kathy's not allowed to answer. What? Volcanoes, yes. Those were big volcanic eruptions in the tropics that put ash into the stratosphere, reflected sunlight for a few years until it was eventually removed. So you can see that both modeled, even without greenhouse gases, and observed temperature dipped for a few years every time that happened. And the fact that the models react about as observed indicates that their response to climate forcings is about right. So this type of graph tells us two things. Number one, we can't explain the recent increase in temperatures without including the rise in greenhouse gases. All sorts of natural factors are included here. Believe me, there's a career to be made if ever a scientist can prove that humans were not responsible for that increase in temperature. And second, it shows that the climate models can represent the real world well enough to reproduce both the general increase in temperature through the 20th century, but also some of the key dips, like when there were volcanic eruptions. Now, I mentioned this was an earlier version of the figure, so again, just sort of from a communication standpoint, I want to show you how it ended up in the final version of the chapter. First of all, notice the temperature scale on the left is in Kelvin, which is very familiar to even those of us north of the border or Europeans who use Celsius. So you might remember, if you've encountered this before, the Kelvin scale increments are the same as Celsius, but the absolute value of 0 is different. Anyway, Americans, of course, 90% of Americans wouldn't know what a Kelvin is if it bit them. So this was the final version converted to Fahrenheit, and also notice all of the lovely exquisite detail about the probability distribution of the models was lost as well. And so now we just have this shading that gives basically the same results. This is a cleaner version, of course, and we can see that the black line, I should also point out there are 4 black curves on here because different groups process the raw climate data differently to arrive at a global average temperature. And so there are slight disagreements among the data sets, but they all show the same basic story. That also has been simplified in this final version. So the future climate change depends primarily on emissions levels, especially past about 2050. So will we continue to rely primarily on fossil fuels as represented by that well on the left, or more on energy coming from the sun, the wind, I was going to say the rain. I guess hydropower is coming from the rain, and the waves. And I'll come back to that point in a minute. Now I'm shifting to the Northwest. So I'm going to sort of go back and forth between the Northwest chapter and the Northwest report, and I've tried to indicate on each slide the source of each figure or statement. So this is the layout. They put a lot of effort, unlike the IPCC, they put a lot more effort into the look and feel of each chapter. So they picked this nice, sort of sunset northwest sky photo for the top. These were the key messages that our chapter team came up with. We went through a risk framing exercise to evaluate what are the main climate-related risks that the Northwest faces. And so the first 3 of the key messages are basically in rank order, our judgment based on available evidence of what the risks are that the Northwest faces. The first is changes in the timing of streamflow related to snowmelt. It turns out if you look at a map of the U.S., at the fraction of annual precipitation falling between 0 and -3 degrees Celsius, the Northwest lights up as having the largest of what we might call the warm snow events contributing to our annual precipitation. So this means that our whole hydrologic cycle is very closely tied with what happens to our snow. And so the changes in snowmelt are already observed and will continue. This has very important consequences for water demand, especially in summer. And in fact, that's a big part of the focus of the Willamette Water 2100 project, looking specifically here in this basin. The second impact area that we judge to be of high concern is the coastal zone, where the combined effects of sea level rise, erosion, inundation, threats to infrastructure and habitat, and also increasing ocean acidity collectively pose a major threat. And we didn't lightly come up with language like that. Some of the existing problems are already fairly acute in certain places with coastal erosion, and the projected sea level rise into the future could do quite a lot of damage in some places. The third main risk area that we identified concerns forests. Again, a lot of this is already observed. I'll touch on some of the evidence in a minute. Wildfire, insect outbreaks, and tree diseases are already causing widespread tree die-off and virtually certain to cause additional forest mortality by the 2040s. I'll just mention that our institute is involved in another research project of similar magnitude to look at forest mortality in the western U.S. In the future, both the biophysical and the economic aspects. And under higher emission scenarios, subalpine forests could be completely converted to other forest types by the end of this century. Now, we did assess the agriculture sector as a factor to be considered and decided that the adaptive capacity of that sector is such that it is probably more resilient to changing climate. Not that it won't be affected, but that so many decisions are made on an annual or up to 5-year time scale that in general growers will be able to respond to changing conditions. I'll come back to that later. There's certainly a lot of areas of concern, but in our assessment it didn't rise to quite the same level. So this is I just waved the report at you, but this is the report. It's available at ocri.net/reports. So this figure, anytime I say Dalton et al., that's referring to the report. Otherwise, it's the National Climate Assessment itself. So this is the regional report. So this is a summary of the projected temperature changes from climate models for 2 different emission scenarios. And you can think of them very roughly as that photo just a minute ago of the windmills versus the oil wells. So the red RCP 8.5, that's sort of the world continues to dig up coal and pump oil and gas and burn them to support all economic growth. Whereas the blue world is a bit more emphasis on renewables and energy efficiency and so on. So again, these individual traces are from separate climate models. The blue ones were all run with the same emissions scenario. The red ones were all run with the higher emission scenarios. And on the left, you can see simulations with these same models of the Northwest's observed temperatures in black. The heavy black curve is the observed. And these have all been smoothed so that you can see the slower variations rather than just all the tiny ups and downs, because those are pretty big for a region like this. So again, for the Northwest, maybe not quite as starkly as for the whole globe, the observed warming kind of lies within that envelope that's simulated by the models. And where we go in the future really depends on the emission scenarios beyond about 2040. With the very, very lowest climate scenario, 2.5 degrees Fahrenheit of temperature change in the future, and that's with a low emission scenario. The very, very highest is close to 15 degrees Fahrenheit. So that's just an unimaginably huge difference between a world not terribly different from the current one and a world just completely different. Just starting with the amount of snowpack left in that high world, there would be very little spring snowpack anywhere in the Northwest, and much reduced winter snowpack as well. So really quite a wide range of uncertainty about the future, depending partly on what the human race chooses to do about its energy. Unfortunately, slides getting cut off. This is sort of a complicated way of talking about the seasonal changes in precipitation. Each dot represents the change in regionally average precipitation, and annual on the left. DJF is pronounced winter by climatologists. MAM is spring, summer, and fall. And the previous generation of climate modeling is shown by the two left-hand bars in each of these. The main point here is that the newer generation of climate modeling really hasn't changed the story a whole lot, although we did find in another diagram not shown here that more recent modeling tends to support a higher low end of climate change. So the new models rule out very low amounts of warming. The main point here, though, is that in each season, the models have, yes, Ryan. This is averaged over the whole Northwest. Yeah, thanks. For each season, there are some projections that it'll get wetter and some that it'll get drier. So unlike temperature, where in every season, every model, it's definitely going to get warmer, there's some ambiguity from the current state of the science about whether a season will get wetter or drier. And the percentage changes here, which is the y-axis, are fairly small. So they're kind of in the noise level for most of these. In other words, a shift of maybe 5% in seasonal precipitation is something that we've definitely encountered before and probably wouldn't notice. Summer probably sees the largest percentage decreases, with some models suggesting decreases in summer precipitation by as much as 30%. And what's not visible on here is the time period. This is a sort of late, I'm just going to check so I don't misstate. This is for 2041 to 2070, so kind of the later part of the middle 21st century, minus 1950 to 99. So ambiguous results on precipitation change. Extreme precipitation, virtually every model, and this is from regional modeling work. So defining precipitation as an extreme precipitation event as an event that happens only once in 20 years or once in 50 years. And these are 8 different regional model combinations. So all but one of the regional models suggests an increase in extreme precipitation for both the 20-year event and the 50-year event. The average of all the models is shown by the plus and the circle right here. So very roughly a 10% increase in the extremes. And this is the same time period, 2041 to 2070 in the future. So summary of the future climate piece. Warming is already underway. How much warmer is uncertain and depends in a large part on the emissions. Every season will get warmer. The precipitation changes are likely to be indistinguishable from natural variability. There are some models that say it's going to get so much wetter that it's going to be outside the range of natural variability. And some that for summer say it's going to get so much drier. And summer is likely to warm more than other seasons. I didn't show that, but that's another robust result from both generations of climate modeling, the sort of mid-2000s era and the most recent. So moving on to water, this is from the NCA Northwest chapter. We emphasize that changes in snowmelt-driven streamflow are already occurring. So this shows the fraction of annual flow occurring in June and the percent change over the 48 to 2008 period in each of those gauges. So the brown circles indicate basins where the streamflow in June has decreased, and that's consistent with the decreased spring snowpack. And you'll notice that the places where there are green or white circles, that is where June flow has increased, are all over on the mild side of the Cascades, so Western Oregon and Southwest Washington. But those changes are quite small, typically just maybe one-ish percent. So the snowmelt-driven streamflow changes are already occurring, as noted. This is a projected future change using set of climate models. And these are the total July through September runoff for the 2040s. So this is from a gridded hydrologic model. So each grid cell is represented as a little pixel. And so we're able to show the stream flow change throughout the basin, not just where there are gauges. But there are notional gauges indicated by circles. So those indicate the changes in flow everywhere upstream of that gauge. And so, bottom line, you see a lot of browns. And the browns for both runoff and stream gauge locations tend to be largest on the, in the Cascades, especially the west side of the Cascades, and also in the mountains of central and northern Idaho. And in some places, the summer runoff decreases 40 or 50%. So that obviously would be a very huge and high impact change. Now, to kind of put this onto a stream flow taxonomy, there are basically three kinds of basins in the region. The first are the rain-dominant basins, represented here by the Chehalis. This set of three panels is actually not in either of the reports, but it's useful for understanding the stream flow responses. So the Chehalis River in southwest Washington is one of the ones where there's almost no snowmelt. And so so this is for October through September, which is a water year. The black curve is the simulated historical flow, and then blue, green, and red are successive changes in climate going into the future, 2020s, 2040s, and 2080s. And this is a rain-dominant watershed. Temperature change doesn't have a big effect, and so you just see very slight changes in the stream flow through the century. This is averaged over a whole bunch of climate models, so obviously if you picked a climate model that had a large increase in precipitation or decrease in precipitation, you'd see some changes. But to first order, the average of all the models is pretty small. A second major type is the snowmelt-dominated basin, for example, the Columbia River upstream of the Dalles. So this is the same kind of plot, and what you see here is the basic shape of the curve doesn't change a whole lot, but you see increases in winter flow and decreases in summer flow, especially in July, August, and September. So if you look at the vertical distance between the simulated historical flow in black and the 2080s flow in red, you start to see those numbers like 25 or more %. Then there are the rivers that are sort of mixed rain snow. The Yakima River in central Washington is a good example. So the simulated historical flow in black has a bit of a fall peak associated with rain, and then as the weather gets colder, most of the precipitation arrives as snow, and so then you get a big snowmelt peak. But as the temperature increases, you see the winter flows going up very dramatically and the summer flows going down very dramatically, so that by the 2080s, the average of the models, and this is for A1B, which is not as large a change as the 8.5 red curves that I showed before, this is now nearly a snowmelt-dominated basin. And the loss in storage that the snowpack represents is larger than the total volume of the 5 reservoirs on this river, and there's a lot of agriculture that depends on this. So this is very similar to a figure that was in the NCA report, figure 21.2a, but shown a little more nicely, I think. So summarizing the water, the effects of warming are already apparent in many basins, and the largest future changes will be in these sort of mild snowy basins, especially the west slopes of the Cascades. Sea level rise, this is not from a report, but I'd chalk it up to another crazy backyard hobby, except he's the world's leading authority on global warming. So everybody wants to know, is it time to build an ark to protect from sea level rise? Well, as Sam mentioned, I've been involved in a number of reports recently. One was a report that came out 2 years ago by the National Research Council on sea level rise on the West Coast. So this was adapted from that report, and it's the projected sea level rise at 45 degrees latitude, roughly the latitude of Newport. And the committee came up with a projection, which is the black curve, but also with ranges, which are represented by the full shading. So the uncertainty in that spread encompasses uncertainties about emissions, about how Antarctica will respond to future warming, uncertainty about how the ocean will respond to future warming, and a number of other factors, including the vertical land movement. As you may be aware, the Pacific plate is colliding with the North American plate, and we're all gradually going away from the center of the Earth at a rate of, I think it's about 3 millimeters per year, which is about the same as global sea level rise. Now, that can't continue indefinitely because eventually the stress on that coastal collision margin will be released in a giant earthquake. The last time this happened was January 1700. The coast of Oregon sank about 5 feet when that happened. So these projections are lower than they would be if that crustal deformation were not happening. And so you can imagine that at some point in the future, you'll suddenly have to add 5 feet to the sea level. But because this report was only about the climate system part of it, all we could do is put a big red asterisk and say these results are valid up until the giant earthquake, subduction zone earthquake. So planners are already using these, but if you want to remember a number, the committee projection for Newport by over the course of this century, all things taken into account, our projection was about 2 feet of sea level rise. But it could be higher than 4 feet or less than 1 foot. So sort of 1 to 4 is the range. Seattle, Olympia, and several smaller cities on the coast of Oregon are all mapping sea level rise and trying to figure out what will get inundated when there's sea level rise plus a storm surge. So city of Seattle has mapped 88 inches. That's the high projection plus a storm surge. And a lot of the industrial area south of downtown Seattle, the Port of Seattle, $1 billion a year or so of commerce goes through there. Very, very big deal. Moving on to forests. Again, climate change is not something way out in the future. The huge increase in forest disturbances has already happened. This map shows the area affected by fire, indicated in orange, and by insects and disease in brown. And this is over a period, the burned area is 1984 to 2009, and the insects and disease are 1997 to 2008. So these are fairly recent things, and you can see that quite a lot of the forested area in the Northwest has been affected. And if we had the data to do a really detailed comparison like this, we know from available evidence that this is way, way more than in any comparable period earlier in the 20th century. And there's a lot of evidence that climate has played some role, maybe not a deciding role in every case, but a significant role in driving these changes. As part of a different NRC report, one of our authors, Jeremy Littell, analyzed data on area burned and compared it with global temperatures. And this is an estimate of the change in the median area burned in different ecoregions for a 2.2 degree Fahrenheit global warming, which is very likely to occur during the first half of this century. So different ecoregions have different levels of response to rising temperature. So the fairly dry parts of central Washington, central Oregon, and southern Idaho, really not much of an increase. As you go up into the headwaters of the Snake River Basin and western Wyoming, you see you get up to this factor of 6 or 7 increase in the median area burned for this amount of warming. So this is built on observed data. There's no modeling involved, but dynamic general vegetation modeling generally confirms that warmer, drier climate will result in large increases in fire. So the main concerns on the forestry sector are the loss of timber production, which has important economic and also community health consequences. The loss of subalpine forests, as noted in our key message, that there's vegetation transformation, especially at higher elevations. But also, every time there's a big fire, and some of these go on for weeks, the smoke causes significant human health effects. And I'll come back to that point when we cover the health. So agriculture as I mentioned, it was one of our 4 key messages. Longer growing season is a positive thing for almost every crop. Drought stress will be an issue in some basins, especially where, just as a reminder, there's the hydrograph for the Yakima River. Some production areas will see large decreases in available water for irrigation. Carbon dioxide fertilization is generally a positive thing for crops. However, it's tempered by the fact that many weeds do extremely well in higher CO2. And in fact, in some experiments where people have grown crops and weeds side by side and added CO2, basically gassed the plants like some kind of future world, the crops love it, but the weeds love it even more, and they're also more resistant to herbicides, which of course is a big deal. There are also changes in chilling requirements for different, especially stone fruit and berries. So sometimes not having it cold enough can make it harder for certain types of crops. And changes in pests. This is a very unknown area. We summarized these impacts on agriculture in this figure, just sort of indicating for different categories of crops how those factors that I just mentioned affected them. So CO2 fertilization benefits are ubiquitous for plants. The upper right there, in case you can't read it, that's milk, dairy, cattle, and calves. So they're obviously very different from vegetation. Reduced availability of water is a factor for all kinds of plants, but not everywhere, because many places rely not on irrigation water, but just on rain that falls. And so there's some uncertainty about how that will play out, and a number of other factors. There's a figure like this in the health chapter of the report, but I redrew it so that the text was big enough that you could read. The general way that health people think about climate is that really, by and large, it's not so much climate as weather that creates health effects. And so if you change the frequency of certain kinds of weather, different things can happen. So air pollution, higher temperature, for example, increases the ozone production in areas with a lot of automobile traffic and so on, some nitrogen chemistry involved there, but it's a pretty clear link between temperature and air pollution. And so the green indicates that there may be adaptation steps that could mediate those changes. Pollen is known to increase, pollen production increases with warmer springs. I know those of you who suffer from allergies probably look back fondly on 2011 and 12 that were kind of cool and wet springs here, and allergies weren't too bad. Microbial contamination and transmission, this is water, food, and vector-borne diseases. A lot of complicated biological and physical environment interactions there. And one here, crop yield, related to the last one. Food insecurity, there's a group here on campus that thinks about rural food security in the Northwest, and it's a concern for human health. So just some observed effects. There was a study by the Oregon Health Authority of hospital admissions and correlating to daily high temperatures. And they found that when the daily high temperatures went up by 10 degrees, there were 3 times as many heat-related effects. Windstorms caused direct damage and fatalities. The famous Columbus Day storm of 1962 killed 46 people. The December 2007 windstorm killed 18. Much better weather prediction, but still not everyone able to get out of harm's way. We know from a study of wildfires in California that there are many more hospitalizations from respiratory problems, and anecdotal evidence suggests the same here, but we don't have quantitative studies to back that up. Our Northwest chapter and also, our Northwest report and also the national report each had a tribal chapter. This is a new and interesting effort. There was a tribal chapter in the first National Climate Assessment Report. But the main points about that are that the world looks very different when you look at it through the eyes of Native Americans. Land and resources are viewed very differently. It's viewed as a relationship rather than something that is used or consumed. And every element of the natural world has some cultural significance. Many of them show up in cultural aspects like songs or stories. And so the loss of those things also has a much more significant impact than for the rest of us. You know, if we go to Freddy's and we end up buying a different kind of salmon than the one we expected to buy just because the coho aren't available that month or whatever, it's, you know, well darn. But not being able to go and actually harvest a salmon in a custom place and time can have much more significance. The tribal chapter in the Northwest report also notes that there are climate adaptation efforts underway by several tribes, for example, the Swinomish, where I was last week. And these, the Bureau of Indian Affairs has funded a large number of climate adaptation studies by different tribes. So just to conclude, we're rapidly moving to an unfamiliar environment. The world has not been this warm during the time that humans walked on it. And so this is a very, very challenging change. Both risks and benefits of change. I've sort of emphasized a lot of downsides, which we can minimize. There are also benefits of change if it's anticipated and planning is robust and vigorous. And as Kathy Jacobs wisely pointed us toward, there's a sustained process of analysis, engagement, and action that will be required to minimize the risks and maximize benefits. And I'll leave off with this. Thanks. So why don't we alternate between questions in the room, and Maria, I believe, is collecting questions online. So start with a question in the room. Yes.
When I look at these charts, they always seem to end at 2100. And what's fascinating is that in many cases you still see this up and up and up. And it seems like there's different time frames in which these models can run. And one of my things is I think about, like, historically, if you look at paleoecology or paleoclimate or paleogeography, and when changes happen that are really massive, I mean, you go like how can anything adapt to that? You have mass extinction events. And so why do we always just end at 2100? Is that just because when these reports are commissioned, it's like that's the planning horizon that we can think about? Does anybody look beyond that? Good question I have.
Yeah, that's a great question. So for those of you online, I don't know, how good is the ceiling mic? Can you pick up? Okay, great. So I don't need to repeat the questions. The National Climate Assessment does largely focus on the period to 2100, but the IPCC report that was released last fall included a number of figures that went beyond 2100. For that very reason, people started saying, what's so special about 2100? As if climate change ends there. I think for very few planning processes does the period after 2100 really matter. I think it matters in an ethical framework where you talk about what kind of world we leave to our children. But there's also the recognition, I think, that the uncertainties are so huge just in how we will bend the emissions trajectory that we can't really say a whole lot beyond there. I mean, to imagine that we would allow, say, 10 degrees Fahrenheit of warming to occur without finally starting to bend it is a sort of discouraging assessment of human wisdom and ingenuity. So maybe those of us who are optimists say that at some point there we'll start to level out just because we realize that it's really a mistake to keep going. But
then it's a lag. Like,
well, right.
The next 20 years, actually, how long do they stay in the model? In other words, how fast does CO2 stay there before there's equilibrium, what does that equilibrium look like? I don't really know because I'm not familiar with this.
Right. One of the points that the last IPCC report in 2007 made is that there's a global warming commitment.
Right.
So if at some point you not just decide to reduce emissions, but if you actually completely cease emissions, there's a committed warming of a few tenths of a degree Fahrenheit, like 4/10 of a degree Fahrenheit. And that's if you suddenly and abruptly stop all emissions. You know, that's impossible unless humans simply stop burning fossil fuels completely and go back to Stone Age life. So given a more reasonable scenario, even very aggressive reductions in emissions would lead to something kind of like the blue curve. You know, so getting it suddenly would still lead to several degrees Fahrenheit of warming. Do we have online questions?
Yeah, there's an online question. This is from David Apel, a freelance science writer in Salem. And he wants to know, how do the hydrologic changes in the Pacific Northwest compare to other regions of the country? It seems like ours might be especially bad.
Yeah, I think that's true for some hydrologic metrics. Northern California is similar in having a large fraction of annual precipitation falling as kind of warm snow. So there have been some pretty big observed shifts in stream flow there as well. One of the things that's in the national report is changes in flooding, and that's actually a very ambiguous picture. And the increases in flooding have been much bigger in the northeastern U.S. than they have been here. So by some hydrologic metrics, the Northwest has not changed as much as other regions. Ann?
To what extent are the dams in the big dams in the Northwest and the Columbia River Basin affected by climate change? And also and the dam operations and reservoir capacities can perhaps mitigate some of the hydrologic impacts?
Yeah, we looked at a couple of studies about hydropower, and you know, the dams, of course, were constructed primarily for flood control, secondarily for hydropower, but then all these other expectations were added onto them: recreation, transportation, and of course flows for fish, or more generally biological operations. And some studies have played around with different ways of managing the Columbia River reservoirs to optimize various outcomes. And it becomes pretty clear when you look at it that way. You know, let's take these reservoirs and the past climate and manage them to optimize economic outcomes, and you can monetize, you know, damage to listed species and whatnot. It becomes pretty clear that the economic value placed by politics to avoiding a flood greatly exceeds the actual economic value of the properties that are being protected. So if you wanted to optimize, you would allow greater flexibility to hydropower production, and you'd put some money into improving levees, and you would tell people don't build in these risk-prone areas. That's, of course, not what's happening. So to talk about how could the reservoirs be managed in the future to mitigate climate change, you kind of have to deal with this conundrum that they're not even being managed well for the present. We didn't wade too far into that in this assessment report. We just noted that in virtually every climate scenario, the annual mean hydropower production as a dollar value goes down. Yes.
This kind of takes off the cartoon you showed at the end, what if we create a better world and there's no climate change. It seems like we're spending a lot of effort and money worrying about the problem, which is, I think it's important to know what the problem we're facing is, but we're not spending much effort to figure out how can we think of a better world. In other words, how can we think, given we're going to have some increase in temperature, so how can we think of a better world given that increase in temperature? So what's Corvallis doing? It's thinking about building a parking garage downtown. Now there's a great climate change thought, you know, that's really a big help. So how can we get people thinking about how to make that better world in the face? We're going to have, obviously, some climate change. So how can we get people, you know, taking the science and thinking about how can we think of that better world and come up with some ideas? And it's certainly, Because climate change, as you've shown, is really a land use issue. And we have to think about how we're gonna use our land so that it's safe, people not building on the edge of the seashore, and how we can grow food and grow crops, and how we can, maybe have fewer roads where people are burning up carbon on them. So how can we think about that better world? How can we stimulate that conversation?
A fair question, and one that I think I will just leave for everyone to contemplate. I think I'm no more qualified to answer that than anybody else in the room. Online question?
This is from Matt McCrae, climate and energy analyst with the City of Eugene. And he says, do we have any sense of where tipping points in the climate system might be, noting that we seem to have just passed one in an Antarctic ice sheet?
Yeah, thank you, Matt. The climate chapter talks a little bit about, sort of non-linearities in the system, but there is no single tipping point in the whole climate system. There was a paper a couple years ago that talked about tipping elements. So individual parts of the climate system may have non-linearities, instabilities, tipping points. We seem to have passed one with Arctic sea ice as well. In 2002, there was a really strong wind event that pushed most of the ice over toward Canada. And so if you remember those maps that I showed, it was the part away from Canada that has lost the most ice. Once that wind event occurred, which was entirely natural, the fact that there was a different energy budget combined with the fact that there was less multi-year ice there meant that it's been really hard to rebuild multi-year ice in that sector of the Arctic. So without the thick multi-year ice, it's very easy for every year the ice to break up, re-expose the dark water, absorb more light. So there does seem to be a threshold that we've crossed there. Many of the climate models that include carbon feedbacks, so forests get drought stressed, they release more carbon into the atmosphere. Those have much larger rates of climate change. And whether any individual forest has gone through a tipping point like that takes a long time to determine. But as I showed, a number of western forests have burned up, and what's coming back, in some cases, very different species. So, yeah, there are probably a lot of other tipping points that we haven't figured out yet. Another question in the room? Yes.
Piggybacking on the tipping points issue, I mean, you seem, you understand the climate science tipping points, but it seems like the most recent IPCC report got a lot more play in the media and in politics. Do you see some of these tipping points in the science possibly leading to some political tipping points, changes in what we actually do in response?
Well, if I thought that more than a very small handful of politicians would listen to a scientist, I'd be a happier person. No, actually, when I was heading off to grad school and sort of thinking, I want to figure out a way to sort of apply climate science in the real world and get into policy and so on. I met with Bob Flegel, who was retiring, and he had spent a number of years representing various sort of atmospheric policy science perspectives. And he said, I think my success rate is about 10%. The times when I've gone back to DC and engaged with a set of policymakers and pointed out either the folly of a given position or the value of another position and the scientific reasons, I said it seemed to make a difference about 10% of the time. I said, well, that's pretty crappy odds. Why do you keep doing it? And he said, well, 10 is better than 0. If I wasn't back there, if nobody was back there engaging, then there would be even worse decisions or even less informed decisions. So, clearly the current administration wanted to use this report to emphasize that the country faces real climate risks now, and to use it as part of its climate action plan. And they have had cabinet secretaries out across the country in different events. Tomorrow, the EPA Administrator Gina McCarthy is going to be in Portland, talking about how do we build a more climate resilient society. So that's a way of sort of having both sides of the conversation. We need to be more climate resilient. We also need to be more sustainable. Maybe another online question?
There isn't one, but I have a question.
Okay, Maria, yes.
You showed that nice example of how the science graph got modified for the general public report. Who made the decisions about how those modifications were made?
The person in charge of our communications was Susan Joy Hassel, who's extremely well known. She's got a training thing that she does. She's written a lot of articles about climate communication. She was focused on the writing, but she also oversaw some of the graphic design. And you know, our chapter, the Northwest chapter, we did our own graphic design. You know, there were several of us who were really passionate about telling the story well in figures, and so stuff we shipped off, they just said, yeah, it looks good. But they clearly put some effort into at least the climate chapter. I'm not sure how many others. Sam.
Thank you. Rick, Phil, if you had to put some uncertainty bounds in the figure that you have projected right now dealing with different models, how would they shift through time, say from 2020 through 2100?
These are the
where we at
uncertainty
right now?
bounds.
Yeah.
I mean, the shading represents the known uncertainties.
Okay. All right, and then also in the previous figure, you had one on energy use with different fossil fuels.
Mm-hmm.
Based on that figure, it seems that even with the that it's unlikely that we're going to be reducing the amount of fossil fuel use back to some earlier time period. All that is projecting increased use of fossil fuels. Is that correct?
This is not a projection. The projections that have been done represent a range of sort of economic and more recently geological factors. I think it's widely believed that the global production of oil has peaked and is probably decreasing, and you know that's just a geophysical reality. Whether coal can be somehow used to make up for that, I mean, oil forms the basis, of course, for virtually all liquid fuels used for transportation, and you can't just convert a car to burn coal. So whether that conversion is coal to oil, basically generating liquid fuels out of coal or switching to electricity or whatever is unclear. But yeah, I didn't include a projected future, but there are lots of diagrams like this that go out into the future and posit different sort of economic factors. Yes?
When you were listing the opportunities for renewable energy in here, you didn't talk about any kind of biogenic resources, and I was wondering what the general attitude or perspective of the evaluation was on carbon neutrality and biogenic sources.
Yeah, I haven't looked at the mitigation chapter, which covers that. I know that in general, corn-based ethanol is a net negative contribution to carbon neutrality. In other words, it takes more carbon to produce and consume ethanol based on corn than it does to just burn the equivalent amount of gasoline. But there, cellulosic ethanol for liquid fuels, and also if you've been following the Boardman plant, Oregon's last coal-fired plant, the legislature required that coal no longer be burned there by 2020, and so Portland General Electric, which owns the plant, is working on figuring out a way to grow giant cane and torrefy it and run the plant on that stuff instead. So that would be a biofuel. So yeah, and there are a lot of other things, and there were there are oil-based biofuels. Biodiesel is made from oil crops or waste oil and so on. So there are a lot of other options. I'd have to go read the chapter to say anything more intelligent. I think we're well past time, so thank you all for your attention, and if you have further questions, I'll stick around for a bit.
Should we announce that this seminar is going to be available online?
Hi.
Tim Davis is that time.
Oh, nice to
Nice
meet
to
you.
meet you. I was trying to take a lot of notes throughout your presentation.